last time we have talked about atoms. So today we are going to continue to talk about elements, compounds, and mixtures. Okay. So in order for us to talk about atoms, elements, compounds, and mixtures and try to understand each of them, we try to relate them to what we see around us every day. In our early classes, we have learned about atom. Okay, so we have learned that every single thing in this world is made up of the same atom. Everything is made up of atom. So it brings us to a question that if every single matter are made up of the same atom, then why aren't all the matters we see around us are the same? Why are they not the same? Why water is so different than steel? Why water or steel is so different than rocks and soil when they are made up of the same kind of atoms? So to understand that brings us to the concept of elements. Echoing the same thing, all atoms are fundamentally the same. Okay, but the way that an atom is organized, its organization, it makes them different. And the different kinds of organization are making up different elements. So in the previous part, we have talked about the atomic number that we see, especially in periodic table. And each element in the periodic table has different atomic number. So this atomic number is the proton number of the atom. And the number of protons actually determine what kind of elements they are. For an example, the three kinds of elements here, all of them are atoms. Okay, but if you look at each of them, hydrogen, helium, and lithium, even though they are fundamentally the same, they are being made up of the same kind of atoms. They have nucleus, protons, and neutrons. They behave the same, remember, with nucleus in the middle. And then we have electron clouds around them. Okay, so it's the same for every single one of them. But they are actually different elements. Hydrogen, helium, and lithium are different elements because they have different number of protons. If an atom has only one proton, it is known as hydrogen. If an atom has two protons, it is known as helium. If the atom has three protons, it is known as lithium. Okay? So currently there are more than 120 elements known as listed in the periodic table. Okay? So we can look at the periodic table together. So, what is element and how is it actually different than atom? So, element is a species of atom. So, an element refers to only one type of the same atom. Okay, they have the same type of atom. Example, copper is made up of only Cu. Nickel is made up of only Ni, so there might be a lot of them, but only Cu or only Ni. And the same goes with oxygen. So this O2 here, okay, oxygen is only made up of the element O. So basically, the elements are the building blocks of molecules. So we haven't talked about molecules yet. Different elements making up molecules are the reason why the matter around us are different. So basically, if you look at what we have covered for now, the concept of atom is the same. Okay, they have nucleus in the middle, they have proton, neutron, and then they have electron cloud or electrons revolving around the nucleus. And it's the same for every single thing. But when we have different number of protons, then we have different kinds of elements. And elements are the things that is making up molecules. So next, we are going to look at what is molecule. Okay, so what is molecules? So molecules is when a combination of two or more atoms, two or more, chemically bonded together. So it has to be chemically bonded together. So if you have more than two atoms chemically bonded together, so that is considered as molecule. So in the previous example, okay, I said O2 is made up from oxygen element. Okay, but because there are two oxygens and these two oxygens are chemically bonded, so this is also known as molecule. So molecules, the atoms making up molecules can be the same type of atoms or different ones. And molecules represent the smallest fundamental unit of a chemical compound that can take part in a chemical reaction. Okay, so this is because as a molecule, as I said, there are more than two atoms, at least two atoms, so they can still be divided further into its individual atoms. Okay, so again, for an example, we have O2. O2 can undergo chemical reaction to form O, for an example. And they still retain the composition and the chemical properties. So there are two classifications of atoms, homoatomic molecule and heteroatomic molecule. So homoatomic molecule is when the molecules are made up with only one type of atoms. Okay, so basically, for example, N2 here, okay, just like O2. So there are at least two atoms or two elements chemically bonded together, but it is only nitrogen. So this is known as homoatomic molecule. The second one is heteroatomic molecule. Same thing, at least there should be two atoms, but there are more than one type of atoms. For an example here, H2O, so we have hydrogen, 2 units of hydrogen and 1 unit of oxygen. So these two are two different atoms. Same thing goes with CO2, carbon dioxide, we have carbon and 2 units of oxygen. So there are different atoms or different elements. Or HCl, we have 1 unit of hydrogen and 1 unit of Cl. So there are two different kinds of atoms. So the molecules can either be homoatomic molecule or heteroatomic molecule. Despite classifying the molecules as homo or heteroatomic molecule, we can also classify them more specifically on the atomicity. Some elements can exist on its own because it's very, very stable. We refer to this element, we refer to this as just element actually. Most of the time, we just refer to them as element. But if they are to be classified as a molecule still, they are known as the monoatomic molecule, meaning only one type of atom. So they are able to exist as is because they tend to react, they tend to not to react with anything, or known as inert. The most common examples are noble gases such as neon and argon gases. If the molecule exists with a combination of two atoms, they are known as diatomic molecules. So di here represents two. Some examples are oxygen, nitrogen, and hydrogen gases. If the molecule exists with a combination of three atoms in a molecule, so they are known as the triatomic molecule. Again, tri here represents three. The most common example that we can see every day is water, H2O. Okay. H2O is made up from two hydrogens and one oxygen. So there are three atoms, even though there are only two types of atoms, but there are actually three atoms. Another example is ozone, O3, where it has only one type of element, but it requires three oxygen in order for it to become stable. Finally, we can also classify anything with more than four atoms, or in general, molecules with a lot of atoms as polyatomic molecule. Elements with more atoms in a molecule. Example, S8, H2O2, and there are many other examples that you can refer to on your own when you do your own reading. So, just quickly, a quick recap. We have understood about atoms, okay, elements and molecules. So atoms is the smallest, okay, is the smallest part of a substance that cannot be broken down chemically. So the key here, of course, it cannot be broken down, but it cannot be broken down chemically, okay. And atoms consist of neutrons, protons, and electrons. So something that we have learned before. We have nucleus in the middle. Nucleus is made up of protons and neutrons. But then outside we have electrons. Okay, so this one unit is known as atom. And if you look at the definition, so if you look at the definition, it cannot be broken down chemically, but some of them, for example, electrons can be moved around, but that is not a chemical process. Okay, so in order for an atom to be classified as an atom, it cannot be broken down chemically. And if you look at elements, okay, so elements is the purest or simplest form of a substance, okay, meaning that it has only one type. Like the example that we've shown before, if you have copper, Cu, you only have copper for the whole thing, okay. And element is distinguished by its atomic number, and the atomic number is actually referring to the proton number, okay. Atomic number is equals to proton number. Okay, so by looking at the proton number, or by looking at the periodic table that displays the proton number, we can determine, or we can identify what kind of element is that. And finally is molecule. Molecules are the combination of two or more atoms chemically bonded together. So and molecules can be a combination of atoms. Let's say combination of atoms, or you can also say same element, for example H2, N2. So all these are molecules because it has at least two atoms, and these two, H and H or N and N, are bonded together. So this is known as a molecule, even though they are also element. Okay, and and sometimes it can also be a combination of different elements. Okay, but you cannot call them elements anymore, but they are the combination of different elements. For an example, H2O, water. So water has element hydrogen and element oxygen, so it's a combination of at least two different elements. Another example is our table salt, NaCl. It is a combination of Na and Cl. Okay, so these are molecules. Just I love to share this, just a sharing. So I'm not sure if you guys have seen this before. This is not like a new picture. This picture emerged in 2017, but I like to show it because it amazes me. So this is actually a photograph of a single atom. So this one here, that one dot there, is actually a photograph of a single atom. Okay. What amazes me is that this photo was not taken by a well-known scientist. It wasn't taken by a big company or by Nobel laureate, but it was taken by David Neglinger. So he was a PhD student, okay, and he simply used a DSLR camera. So it's a very common DSLR camera, and he peeked through a window of the ion trap's ultra high vacuum chamber. Okay, so this is an ion trap. So basically the atom was sort of trapped in between those two what do we call that, ends. Okay, so he wasn't doing this experiment. He wasn't actually doing his PhD in this particularly, but he was just doing it out of curiosity. He came to the lab on the weekend and dared to try it out. Probably, no matter how stupid it sounded in the beginning. So again, what amazed me as well is that this photo won the overall science photography prize by the UK Engineering and Physical Science Research Council in 2017. In his experiment, he held this atom. Okay, this atom was held nearly motionless. It's not entirely motionless, but nearly motionless by an electric field emanating from these two metal electrodes. So these two metal electrodes, both of them emanates electricity, and the electric field holds the atom. Okay, and the distance between the ion trap's small needle tip is less than 0.2 centimeter, less than 0.2 centimeter, or 0.08 of an inch. And then the atom was actually still not visible, but it was then illuminated with blue violet light. Okay, so it was illuminated by light, so it emits certain light that it was able to be captured using the DSLR camera. So if you look again, I'm zooming in. If you look closely, so this is the atom illuminated by the blue violet light. And as you know, atom is very, 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 very small. If you remember in the early classes, we learned that one atom is only about 2 angstrom. Okay, so it's very, 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 very small. But still, I don't think we can actually see 2 angstrom, but then the only reason why we can see the atom in the photo is because it absorbs and re-emitted laser light at a speed capturable by the DSLR or long camera exposure. So the photo is actually of the laser light being re-emitted. So basically what happened was the atom, it absorbs the blue violet light, and then it emits the light, and that light emitted was the one captured in this picture. So it's not actually the outline of the atom. So if you look at it closely, the outer line of the dot is not actually the outline of the atom. So it's just the outline of the light emitted from the atom. So it is probably larger than 2 angstrom. And without the long exposure effect, the atom wouldn't be visible to the naked eye. What else about this picture? So the atom that is actually being captured is strontium ion. So this is strontium ion, Sr, with a proton number of 219. Okay, so strontium, it is an atom. So it is an atom, but as I said, it is also an element. Okay, so you have to be clear of that. Its atomic number is 38, or in other words, it has 38 protons, and the size is 219 billionth of a millimeter across. So strontium atoms are relatively large by comparison to most of the other elements. That's why you can see like this side, it's quite larger as compared to other atoms. Again, I am very amazed by this photo, because one is that it's an amazing photo. It's actually, I think, amongst the first to capture a photo of an atom for the first time ever, and to deliver a point that anyone can be great at something in their life, especially when curiosity and efforts are channeled the right way. Okay, so next we are trying to understand matter around us. So we are going back to the original thing that we were focusing on, is to understand matter. And in order for us to understand matter, it's not enough by just understanding atoms and elements, but we are going to learn about compounds and also mixture. Okay, so this is because matter in general can be classified into 3 types based on their atomic makeup. So you have learned elements and molecules, but molecules is not the classification. So the first classification is yes, element. Okay, so elements are matter composed of only one type of atom. It could be monoatomic, it could be diatomic. Okay, so for example, as I've said before, it can be, for example, copper, or it can also be H2, for example. So all those are elements. Okay, the second classification of matter is compounds. Okay, so compounds are matters are composed of 2 or more different elements greater than 2 that are chemically bound together and do not vary in composition. So these 2 are very important definition of compounds: chemically bound together and do not vary in composition. On the other hand, the next classification is mixture. So mixtures are matters composed of 2 or more different elements, still greater than, equals or greater than 2, that can vary in their parts by mass. Okay, so basically compounds that have a specific ratio in between the 2 elements But mixture, it doesn't have a specific ratio. It can be in different ratios. Okay, so let's proceed on. A little more on compound. So a compound is a substance which are formed by two or more different types of elements, again two or more, which are united chemically in a fixed proportion. So this is something that I have explained in the previous slide. Two or more different types of elements, okay, because if they are the same, they are still elements, but they are molecules. But this has to be different types of elements, okay, and they are united chemically, so there must be some bonding, and they have a specific proportion, okay. For an example, the easiest example is water. Okay, so water is very specific. Okay, water always have two hydrogens and one oxygen. So they have two or more different types of element. We have hydrogen and oxygen. They are chemically united. All the hydrogens are attached to oxygen chemically, and the ratio between hydrogen and oxygen is always fixed 2:1. Okay. Compounds have their own unique set of chemicals and physical properties. Okay, and the properties of the compounds are distinct or unique or different than the elements from which they are. Okay, again, the easiest example is H2O. Okay, so let's say if you break them down, okay, let's say if you think of water, H2O is a liquid at room temperature. Okay, so that is one of the property of H2O. But then if you break them down, let's say you get H2, okay, H2 is gas at room temperature. So the property of H2O is different than the property of H2. So distinct or different. Okay. And all compounds are molecules, but not all molecules are compounds. Okay. For example, water, H2O, as the example that I've mentioned before, and ACl, for example. So there are compounds, and there are also molecules. So all compounds are molecules. Let's say H2O, H2, all of these are compounds, and also, sorry, H2 is not compound. So all of them are compounds and molecules, but not all molecules are compound. So example, N2, H2, so they are molecules, but they are not compounds, okay, because they are made up from the same type of elements. So you should be able to distinguish between each of these. I just want to share some examples of common compounds in everyday life. The first one is baking soda. So it's very easy for you to find baking soda, right? So the chemical formula of baking soda is NaHCO3, or sodium bicarbonate ion. Baking soda or baking powder is a compound consisting of sodium, hydrogen, and CO3, carbonate, or carbon and oxygen. So it is used in baking cakes and desserts, breads, cakes, desserts. It is also used in neutralizing stomach acidity. Okay. Moreover, it can also be used as a natural deodorant. The second example of common compounds is vinegar, or also known as the ethanoic acid or acetic acid. Okay, So its chemical formula is CH3COOH. Okay, it is the chemical compound consisting of carboxylic acid. So carboxylic acid meaning it has CH3, C double bond O, OH. Okay, so that is carboxylic acid. It is widely used as a preservative and for seasoning food and salad. Okay, it is also used for cleaning purpose and also in beauty routine. The next one is aspirin. Okay, so aspirin is also known as acetyl salicylic acid. Okay, this is its chemical formula, C9H8O4. Okay, aspirin is one of the most common medicine we have heard since childhood. It is used to treat pain, fever, and inflammation. And just sharing a little bit of history, like long time ago, people discovered aspirin because those people who are going for childbirth, they are biting on certain tree trunk. Okay, so initially they didn't know why is that tree trunk helping them to like reduce the pain, but actually it reduces the pain because aspirin was available on the tree trunk. Sorry, it's on a willow bark. It's here actually. Okay, so basically they started discovering aspirin because it was extracted, it could be extracted from willow bark. So as you know, aspirin can be used to treat pain, fever and inflammation, and it is also a major component of many other medicines. The last example that I would like to share is acetone, CH3COCH3. So acetone is a very common solvent. It's actually a ketone because it has CH3, C, double bond O, and another CH3. Okay, it could break down nail polish, and it can be used to remove gum, oil, or other sticky substances from textile. So this is a very common solvent, and it is also a very common ingredient in a detergent. Okay, but acetone can easily mix with water. If you mix it with water, it can dissolve easily and evaporates quickly in the air as well. Okay, so just a quick video that I would like to show. So basically you can also watch this video on your own. I'm going to put it in the spectrum, but this video, it shows a few compounds, sorry, a few options, and you have to classify whether those are elements or compounds. So let's look at some of them. So hydrogen, you have to guess, hydrogen is an element. It's not a compound, so it falls under element because it doesn't have more than one type of element. And O is a compound because it consists of more than one type of element. It has nitrogen and oxygen, and they are chemically bonded together, and they are in a specific ratio. O2, even though there are two atoms, but it is the same types of elements, so it should fall under elements. N2, for the same reason, should fall under elements. Cl2, again, for the same reason, should fall under elements. Water is made up from two different types of elements, so it has to be compound. Nitrogen dioxide, one nitrogen, two oxygen, again it is a compound. Okay, two different types of elements, chemically bonded, fixed ratio, and the same goes with CO2. For the same reason, CO2 is a compound. So you should be able to distinguish between elements and compounds. Okay, next, let us look at mixture. Okay, a mixture is a mixture is a is when more than one substances, such as molecular compounds, mix with each other without participating in chemical change. So what does that mean? So let's say if we have a beaker, okay, and then you mixed two kinds of elements together. So you put in the first element, the blue one, and then you put in the second element, which is the red one. Okay, but these two elements, they do not undergo any chemical processes. It doesn't form a new chemical bond. It doesn't do anything. It just mixes together. So it just mixes with each other without participating in a chemical change. So this is known as mixture. In other words, they are not combined chemically. Okay, therefore the physical and chemical properties of mixtures reflect those of the elements and compounds from which they are made. So for example, in this case, its physical and chemical properties reflects the red one as an individual element, and also the blue one as the individual element. Okay, so it doesn't form a new bond, it doesn't form anything new, so it doesn't change the physical or chemical properties. In mixtures, separation of components can be easily done, usually by physical method. For an example, if we have salt water or seawater, okay, so in seawater, of course, you have a lot of H2O molecule, but then because there is salt, there is also NaCl. But NaCl is not chemically bonded with water, so NaCl is just like a mixture in the water, so it can be easily separated by evaporation process. So by evaporation, you can actually get NaCl, pure NaCl. Okay, so that's the easiest example of a mixture. And the proportion of a substance vary in an indefinite manner. For an example, if you have two different Cs, one C might have a higher content of NaCl, the other C might have a lower content of NaCl. Therefore, we cannot specify the ratio between NaCl and H2O. So that is another characteristic of a mixture. So the first example that I want to show is seawater. So we have discussed this in the previous slide. So seawater, it's actually a mixture of pure water and dissolved ionic substance such as sodium, chlorine, calcium, magnesium, and sulfate. So in some places, as I said before, the percentages can be different. Some places high, some places lower. So that's why it is a mixture. Another example of a common mixture that we can find in our daily life is crude oil. So some people might think that this is a compound, but this is actually just a mixture. So crude oil is actually a mixture of organic carbons, okay, and they are made up from mainly hydrocarbons such as paraffins, naphthenes, kerosene, diesel, bitumen, and all of them are not having any chemical bonds. There's no chemical, they are not chemically connected together. So as I said, they are a mixture. So in crude oil, you can also find organic compounds of sulfur, oxygen, and nitrogen, and some metallic compounds such as vanadium, nickel, and sodium. The next mixture is air. So this is something that again we have talked about it before. So it's a mixture of different gases, and they are not having any chemical interactions together. And finally, another example that I want to show is ink. Okay, ink, you might think that ink is a compound, but it's actually not. It's a mixture where it can be easily separated. So the process of separating ink is known as a chromatography process. Okay, so I'm going to show that in the next slide. So there are three videos that I would like to show here because I want to relate the concept of separation in order for you guys to build the right concept of a mixture. So in the first video, this is actually the fractional distillation of crude oil. Okay, wait up. In the second video, this is actually the
separate -7°C and past fractional temperatures. Therefore, it's used in pure
separation of air.
oxyacetylene fluid argon to 183 degrees
So there
Celsius.
are a few
The
processes that
oxygen
is
boils
involved
off.
in the separation of air, but
Now,
it can be done
pause the
easily.
video and
And
think of
in the
another
last video, this is the chromatography technique of a separation in ink.
Insert that chromatin pigments number
Okay,
for each.
so I'm going to include this in the Spectrum. Each of the videos will be available on Spectrum, so you can watch it on your own. Okay, so as I said before, the first one is the separation of crude oil. Okay, so this process is known as the distillation or fractional distillation process, and this is done by boiling them because each of them has different boiling point or BP. The second process, fractional distillation for air separation. So this is air separation. Okay, it is actually done first by liquefaction before fractional distillation. Okay, so it involves both. Liquefaction requires heating it up, so you are actually playing with temperature to turn to liquid. Okay, and then you use the concept of distillation, the same as crude oil, where each of them have a different boiling point. And the last one that I'm showing here is the separation of ink. Separation of ink, and this is done by chromatography technique. Okay, so and for all these processes, all of them still retain their original individual properties. Okay. Mixtures can also be divided into what we call as a homogeneous mixture and also heterogeneous mixture. This is just what we can see with our naked eye. So for homogeneous mixture, it appears uniform to the eye. Therefore, it is also described as having only one phase or single phase. And because it is uniform throughout, chemical composition is the same upon any part of sampling. So let's say if you have a beaker, let's say this is a beaker, and you have a mixture. If you sample it from here, or you take from here, or you take from here, you should get roughly the same chemical composition. Heterogeneous mixture, on the other hand, is the opposite of that, opposite of homogeneous mixture. So it is not uniform. It can be separated by mechanical method, example, filtration. You might get different chemical composition within sampling. For example, if this is a beaker, if you sample from here, you might get more of the purple ones, but if you sample from here, you might only get the green ones. Okay, so that's the difference between homogeneous mixture and heterogeneous mixture.